LaGrange multipliers. Let's take a look at this. I did this problem. Yeah, sure, fine. So let's actually skip this one because that's sorry, I thought I had a thing all queued up here. Let's go ahead and start with something not terrible. Sure. To find the dimensions of the largest rectangular box that can be mailed through the US Postal Service. You might think, well, James, whatever, but there's actually some requirements. That is the length plus the girth must be less than or equal to 108 inches. Okay. So whenever you're doing a problem that you either recognize or don't recognize as Lagrange multipliers, there's always going to be two things to look for. One, the thing you're trying to optimize, either maximize or minimize. Two, some sort of constraint or limiting factor. In this problem, in fact, it'd probably be good to draw a picture before I get going any further. So here's my box that I'm going to mail. I could draw the back part here. And if I label the sides typically like this is X, this is Y, and this is Z, when we are trying to maximize the volume, which is equal to just X times Y times Z, which if you're thinking Lagrange, the thing you're trying to optimize, we typically call little f of however many variables you've got, f of X, Y, Z. And then we have our constraint or limiting information. So this box has to meet some requirements. The length plus the girth has to be less than or equal to 108 inches. Well, if you're trying to maximize the volume, you're not going to make your length plus your girth 100 inches. You're going to use all 108 inches you've got. So we know that we want the length plus the girth. I don't know why I wrote length but not, or wrote girth but not length. We want that to equal 108 inches. What is the length? Well, it's whatever we decide it's going to be. We can say that the length is X or Y or Z. It's just one of those three dimensions. I would make it Z. Usually, if you got something to make a choice to be kind of like the odd man out, Z is usually the one that I kind of pick to be the one that's different than the others if the others seem the same. So we're going to say that the length, which is Z, plus the girth. So if that's the length, the girth is the around dimension or the circumference essentially. Let's draw it in red here. So if Z is my length, then here's my girth. That length of that red around the measurement box. So X plus Y plus X plus Y, or 2X plus 2Y. One defining feature of a constraint versus, so the thing you're trying to optimize is just like X times Y times Z, or 2X plus 2Y, or something X's, Y's, whatever, not usually equal to another number. Whereas the constraint is some also function of X, Y, and Z, but it is equal to some value. So that's a good way of identifying the thing you're trying to optimize versus the thing that is your constraint. So there's my constraint. I would leave it like this personally, but I know your teacher, I think she prefers to bring everything to one side. So we could also rewrite this as in the more kind of typical way, 2X plus 2Y plus Z, just writing the variables in the usual order, minus 108 equals 0. And we would call this our G of X comma Y comma Z. So usually the constraint equal to 0 is our G function, and the optimization function to optimize is our F function. And then we use the Lagrange multipliers method. So there's a couple ways to do this. The way I think you've been seeing in class is by setting capital F of X comma Y comma Z comma lambda equal to little f minus lambda times g, which in this case, little f is just our xyz. And lambda times g is going to be the 2x plus 2y plus z minus 108. After we do this, I will mention another way of seeing it, because I've had a couple people mention to me, but this is a perfectly fine way of doing it. After you do this, just like with finding critical points in general, we're going to take all the partial derivatives and set them equal to 0. Same as with the other method where you find like fxx, fyy, fxy, that kind of thing. We still find the critical points by setting the partials equal to 0. Yeah. Oh, you could. So the notation I've learned at one point is capital F. It is totally fine to use capital L or really whatever you want. But if she's using capital L in class, I can certainly use capital L. I'm used to most. If you look at other textbooks, I have seen they use a capital F of XYZ, but it's probably because she's probably seen that too. Capital L is a better choice for LaGrange, and also to not confuse capital F with little f. So I think that's a perfectly fine choice. But whether you could call it capital Z, or capital Z is probably a bad choice here, but some other letter we're not already using. You can call it I think someone else calls it capital gamma. So really any letter is fine. I would use something you've already seen in class. So then we're going to find all the partials. Well, we'll talk about the last one. So the partial with respect to x is going to be 1 times y times z. For the partial here, the lambda just sticks around, and you get minus lambda times the derivative of whatever is in here with respect to x, which is going to be 2. And we set that equal to 0. Same deal for the rest. Partial with respect to y is going to be x times 1 times z minus lambda times 2. And finally, partial with respect to z is going to be x times y minus lambda times 1. Do be careful. I have made this mistake in the past. My z's and my 2's often look pretty similar. So make sure if you have 2's in there that you're accurately distinguishing between them. I was doing this problem or a problem like this the other day with someone else, and we got really messed up because we accidentally changed the z into a 2. So just be careful with the z's and the 2's. That's why I try to make my z's with a little horizontal line like that, but sometimes I miss it. Now, what I will say here is you don't really have to find L lambda. Here's why. If you find L lambda, it's going to be 0 minus 1 times 2x plus 2y plus z minus 108 equal to 0. And if you multiply both sides by -1, you really just have 2x plus 2y plus z minus 108 equal to 0. I'll just point out, L lambda is just your constraint equation again. So this is just the constraint. We are going to use it, but my point here is you don't really need to write this because you already have this piece of information somewhere else. Questions so far? Cool. The next part is the part that's kind of a grab bag. At this juncture, you usually are trying to, in my opinion, get however many variables you have, all but one of them in terms of the other one. So in my opinion, we are trying to get x in terms of y and z in terms of y. Or take your pick, x in terms of z and y in terms of z, or both of them in terms of whatever you want. Usually it ends up being in terms of y if you use the first 2 equations and the second 2 equations. That's just kind of how it usually falls out. There are other ways of doing this. There are lots of ways of doing this, actually. Some people do this weird thing, like I've seen other people do this thing where they take the first equation and they divide it by the second equation. That's totally, that's not quite valid because I got zeros on this side. So some people I have seen do this. I'm not going to do it this way, but I'll show you. Taking these first 2 equations, call this 1, 2, and 3. If I first solve them both, so yz equal to lambda times 2 and xz equal to lambda times 2, which I could write as 2 lambda, but I didn't. You could divide these by each other and get y divided by x equal to 1 or y equal to x. That's something people do. Do I like doing it? No, I don't. But some people really like it because it feels easier to them. What I would do is solve them both for lambda and get lambda equal to yz divided by 2 and lambda equal to xz divided by 2. And then set those equal to each other. That's a more typical way, in my opinion. Setting those equal to each other, we're going to get yz over 2 equal to xz over 2. I'm a big fan here of cross multiplying. You do not want fractions after you've set them equal to each other. So then 2yz, I mean, really, you could get rid of the 2's also. 2yz equals 2xz, divide both sides by 2z, and you get y equal to x. But really, there's a lot of ways to get there. So then pick any other two equations. So don't pick 1 and 2 again. Pick 1 and 3 or 2 and 3. Those are your choices. Usually people will end up writing 2 and 3 just because it feels convenient. So using these two now, I'm going to have x, z, be careful copying stuff down. It's easy to miss something. Xz equal to 2 lambda, holy smokes. Let's just try that again, James. Xz equal to 2 lambda and xy equal to lambda. So that means lambda is going to equal xz over 2. And lambda is going to equal xy. Setting those equal to each other, you get xy equal to xz over 2. Multiply the 2, divide both sides by x, you're going to get 2xy equals xz, or 2y equal to z. Here's the easiest way to proceed. In both of these things, or both of these equations, what variable is showing up both times? X, y, or z? Y. So the one that's showing up twice is the one you want to write the other ones in terms of. So I've got x as a function of y, and z as a function of y. That's great. I'm already set. But like if this had been like 2z equal to y, I would have had to divide both sides by 2 to get z equal to y over 2. So you're trying to basically solve for the ones that are not showing up twice. So you get z, y, x equals a function of y, z equals a function of y in this particular case. After this, then you're going to take both of those. So y equals x and z, or x equals y is what I should have said, and z equals 2y, and you're going to plug those in to the constraint. So plugging back into the constraint, which is just L lambda, you're going to have 2 times, well, x is now y, plus 2y, plus z is also 2y, and I prefer to say equal to 108 as opposed to minus 108 equal to 0. Or add this together, 6y equals 108. That means y is going to be 108 divided by 6, which is equal to what? 18, I think. Yeah, that sounds right. 18. And then going back here, if y is 18, that means x equals 18. So x is going to be 18 inches. Y is going to be 18 inches. And z is going to be 2 times y, which is going to be 36 inches. Now, here's the disappointing piece of information. We don't know if this is a maximum or a minimum. It could be neither. It could be a minimum with to find a maximum. Usually, if they're asking you to find a maximum, you will have found a maximum. But if they ask you, is it a maximum or is it a minimum, it's usually not very easy to tell using LaGrange multipliers. Sometimes you can kind of plug in the point and see that if you plug in something else that's close, that is going to be either smaller in this case. Like if you pick other values that met this condition, like for example, if like x were 20 and y were 20, that would use up 80 inches of my 108 because, right, I've got 2x and 2y, and then I'd be left with 28 inches for my length. And if you compare those, this product is bigger than that product. This has more volume. But really, LaGrange, that is one of the downsides of LaGrange multipliers, is you don't really get given a good way to find if it's a max or a min. Questions about this before we do another example? So let's do a homework problem because the homework is weird. So let me grab the homework here real quick. Find it. I know I have it. I know I brought it with me. And like most things I know I brought with me, it's impossible to find one to actually want to find it. There we go. I think I found it. Yeah, right there. So looking at the homework section, specifically 10.6.2, right? Yeah. So yeah, these are interesting. You have one in mind, or you want me to grab one? Okay, cool. I'll just grab one. So you're asking the wrong person. I cannot tell you because I do not know. I would, so actually, there's something in the chat here, but let me take a quick gander at her. Can we do 10.6.2 problem number 2? Yeah, we can take a look at that one. And then I'll look at the midterm to see what hers look like, and we'll kind of try and do one like that. 10.6 number 0.2 number 2, which is actually the one I was going to pick anyway. Awesome. So 10.6.2. So use LaGrange multipliers to find the absolute extreme. Okay, sure. Of f of xy equal to 4xy, subject to the constraint x squared plus y squared equal to 9, or I would prefer to write this as x squared plus y squared minus 9 equal to 0. That's our g of x, y. So, oh, sorry. And what do I really? Yeah, I kind of want to show you all. Let me think for a second here. Yeah, and I think this will have a. I think this has a maximum and a minimum. So here's the idea. Yeah, we should let's look at the graph of this for just a second. Although you wouldn't normally like do it this way, because it's hard to graph these things. Oh my gosh, can you minimize though? Maybe not. Sorry, I'm all in the way here. Cool. So I didn't want GeoGebra. I like the Desmos. The new Desmos 3D one is, I think, pretty good. Yeah, sure. Yeah. So first, I'm going to graph the thing that I'm trying to maximize. So I'm going to have, I would just write z equals 4xy, which is a saddle. It's actually a saddle, but it's been like, so you normally when I think of a saddle, I think of like x squared minus y squared or y squared minus x squared. This one is that it's just been like rotated 45 degrees in the xy plane. Not a huge deal. And then our other equation is x squared plus y squared equal to 9, which you might recognize before I graph it as what kind of equation? It's a circle, except in 3 dimensions, it's a cylinder. Because if you've got a circle, z can be anything. So you can go up or down as much as you want. Oops. So I really like this feature on Desmos 3D, is they'll give you just the 2-dimensional graph, but then if you want to make it a 3-dimensional thing, extend it in the z direction, you just click this little button here. There's your cylinder. So now the idea is we're basically saying where on the red surface that happens to intersect the blue surface is the red surface having a maximum value or the red surface having a minimum value. And you might have to zoom in or out. Can I? Maybe. So maybe. Okay, so it's hard to kind of see, but if you look right there, it appears this function has, right, that red function is as big as possible while still being on the circle where x squared plus y squared is equal to 9. That's kind of, now I know that this is not how you're actually going to do it, but that's the idea. You're saying, I've got the surface, and in the xy plane, if I'm just in the circle, where on that surface are things the biggest, where on that surface are things the smallest. So the surface might be, subject to this sort of constraint. Also, if you look over here, that's why, whoops, stop rotating. If you look, calm down. If you look down there, that's probably where the minimum is. So it looks to me, there's probably going to be 2 minima and 2 maxima. Probably. We've probably got something that kind of looks like a very, what would I say here? There's a word I'm looking for, a very stretched out Pringles potato chip. Right? If you think about the Pringle shape, if you made it really, really vertical, you'd have like the end parts that are kind of the up parts and the middle parts that are kind of the down parts. That's what I think we've got there when you've taken, and it's just the edge of that, I guess, really is what we've got. Okay. So we've kind of visualized what we've seen, what we think is going to happen. Now let's try and actually do it, which, okay, we'll see how this goes. So we start off with, I know what the other thing I was going to say for that previous problem is most of the time you should do it this way. L of x, y, lambda is equal to the thing you want to maximize minus lambda times the constraint. What I want to mention, though, is that you could also do this as taking your gradient of f and setting it equal to lambda times your gradient of g. You shouldn't do it this way unless you really, really, really prefer to do it that way, but they're literally the same thing. Let me show you what I mean. When we find Lx is going to be 4y minus lambda times 2x equal to 0. Ly is going to be 4x minus lambda times 2y equal to 0. And I will just point out that if I found the gradient of f, well, the gradient of f is 4y in the first component, 4x in the second component. Lambda times the gradient of g is 2x, 2y. So here I'm setting 4y equal to lambda times 2x. And over here I'm setting 4y equal to lambda times 2x. They're the same. It's just a different way of expressing the exact same content. So if you like this over this, that's totally fine. They're the same thing. Because some people would ask me about that, so I just want to clarify. It's really the same work. All right. I feel like let's take a look here. So I'm going to solve for lambda like I usually do, although sometimes that can be dicey. Yeah, question, Jocelyn.
So should we always start with Ly and Lx to find one of the variables and then that?
I don't want to, but I'm going to disappoint you right now and say there is no tried and true one way of solving LaGrange multipliers every time. It's really just kind of like, what do I think I can do with this? My usual go-to is to solve everything for lambda, but sometimes you have to do something else as well. So, and I will point out, well, not I won't point out, that's not right. Yeah, no, definitely not yet. Sure. So solving for lambda, I get 4y equal to 2 lambda x, which gives me lambda equal to 4y over 2x, which is 2y over x. And then over here, same deal. I get 4x equal to 2y lambda. So I get lambda equal to 4x divided by 2y, which is just 2x divided by y. Then I set this equal to each other. So I've got 2y over x equal to 2x over y. Cross multiplication is the way to go here. So y squared equals x squared, which gives me, well, I dropped the 2's because I couldn't help myself. 2y squared equals x squared, y squared equals x squared. And you probably don't want to do anything else here. You don't want to say y is equal to the absolute value of x. Also, look at where we're going to plug back into. What's my constraint? Do I need to solve for y? No, I can just say, instead of saying x squared plus y squared equals 9, take what y squared is equal to and get x squared plus x squared equals 9. So 2x squared is equal to 9, or x squared is equal to 9 divided by 2. So x is going to be plus or minus the square root of 9 over 2. Which, if you're typing it into web work, is probably the easiest way to write your thing. If you simplified this, it'd be plus or minus 3 over root 2. We rationalize, it's plus or minus 3 root 2 over 2. But honestly, this is probably the easiest way to write it. Okay, so if x, so let's talk about how many critical points we're going to get. You know how many we're going to get? 4. Because if x is positive root 9 over 2 and y squared equals x squared, well, y could be positive root 9 over 2, but y could also be negative root 9 over 2. So that's going to give you y equal to plus or minus root 9 over 2. And the same thing is true if x is negative. Right? If x is negative root 9 over 2, y could still be positive or negative. So essentially you have every possible pairing here. Positive, 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 negative, 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 positive. For ones like this, where you have more than one critical point, it's usually ideal. Because then you can, I think, justify to yourself, well, if I plug something in and it's the bigger value, it's probably a maximum. If I plug something in, it's the smaller value, it's the minimum. So let's go ahead and take a look here. If I plug in, sure. So I will just point out that f of xy is 4xy. So this is actually going to turn out pretty nice. So if they're both positive, so root 9 over 2, comma root 9 over 2, I'm going to get 4 times the square root of 9 over 2 times the square root of 9 over 2. So that's going to be 4 times 9 over 2, which is 18. And that's true if they're both positive or if they're both negative. If they're both negative. So yeah, that's kind of terrible. Here, I've written this in a way that's supposed to imply that the signs have to be the same. I know it's kind of annoying, but I'm lazy. Or if the signs are opposite, so if you have f of, say, positive root 9 over 2, comma, negative root 9 over 2, you're going to get the same value, but everything's going to be negative because it's a positive times a negative times a positive. So that's going to end up being negative 18. And that's true whether the first one's positive and the second one's negative, or the first one's negative and the second one's positive. So to answer the question that was actually asked, we would say there's an absolute maximum value is equal to positive 18, and it occurs at the points positive root 9 over 2, comma, positive root 9 over 2, and negative root 9 over 2, comma, negative root 9 over 2. And similarly, we have a negative absolute value, or an absolute minimum value of negative 18 at the positive negative and the negative positive column. And just to really satisfy my own curiosity, if we look back at the graph, which I'm sure I didn't just close it. Oh, good, I didn't. I think we can even just plot a point here and say, let's see. So if I do square root, I don't want to do the square root. Let's just be smarter about that. 9 over 2 to the 1. Oh, come on. Do better than that. To the 0.5 power, comma. Sure. Same thing. It's getting dicey over here. Too many parentheses. Oh, Jesus, holy smokes. Sorry. Will you show me where that point is? It might. Let's see here. It should be over. Maybe. It should be where they're both positive. Look, there's that point. And if we throw in a z value of 18, haha! Look at that. Right where we thought it was supposed to be. So really, the thing we talked about before really does make sense. You're saying on this red surface, restricted to the blue equation, where does this function have a maximum or a minimum? Awesome. I love this. This is great. Cool. All right. Questions about any of this? Yeah. Mm-hmm. Mm-hmm.
How do you know what equations to plug in?
So I'll say two things. Thing one, usually you don't end up having to solve for lambda. You can, and sometimes you do. Most of the time you don't. So usually I'm trying to avoid getting lambda equal to any real number. Second thing, once I've got like y in terms of x, or in the previous one, z in terms of y and x in terms of y, I'm plugging all that back into the constraint. That is the equation that's already give you that. I should say that is the only equation I actually have. Right? There's my equation where something is equal to something else. All these other partial derivatives are just helping me find the critical point, or one of the values for the critical point. And then this equation is saying, oh, well, once I've got my x value, now I can use this only equation I have that's limiting me in some way to find the other one or two variables for that particular value of x. Oh, you mean like when I plugged it back into this here? Yeah, so because this question asked me for not only the where is my maximum, I would say, so if I was answering this question using language, I would say I have 4 critical points. One of my maxima occurs at the point root 9 over 2, root 9 over 2. The maximum value is what you get when you plug that back into the function, which is 18. So the maximum value or the minimum value is always what you get out of the function when you plug in your critical point to that function. Whereas the maximum or minimum occur at the critical point that you have found. So the where is always the input, the value or the what is always the output. Okay, let me scan these practice exams real quicker just to see what the LaGrange questions look like and see if there's anything else we should say about that. Sure. On a closed boundary? Well, so we just did that here. This question, the question was find the absolute maxima and absolute minimum. That's it. So you can say absolute extrema, or that's the easier way of saying both things, or you can say absolute maximum and absolute minimum. But extrema is just encompassing both of those things at once. So let's see here. Looking at the practice midterm 1-3, I don't see a LaGrange question. I see a find and classify all critical points of a function. Oh, sorry, I didn't see the last page here. Sure, find 3 positive numbers. Sure, that one doesn't look too terrible. Let me look at looks like here. And that one looks a little bit, I think so. Oh yeah, question.
So let's go over the practice exam, the last one.
Let's see. Sure, let me see which one that is. So I'll point out, as far as all these go, I would say the one that's actually on the midterm that she gave is the one that requires the most thinking, because all these other ones say, you know, maximize. Well, actually, I think actually 2 probably also requires more thinking. Yeah. So the ones on practice exam 1 and 3 are use LaGrange multipliers to find 3 positive numbers that satisfy this, whose product is maximum. So we're trying to maximize x times y times z, and our constraint is given to us right there. That seems like you're being relatively straightforwardly given the 2 functions. Same thing for practice exam 1-1. You're trying to find the maximum and minimum values of this function subject to that constraint. They're just saying what f and g are without making you work for it at all. But looking at the practice exam and the actual exam she gave over here, I point out that seems like that might not be what you're actually going to see. Yeah. Well, so let me say the thing you're trying to, well, they do tell you what you're trying to maximize there, right? They say maximize the product. They don't actually give you the product, but it's x times y times z. And the constraint is so the constraint is always going to be an equation, some stuff equal to a number typically. Whereas the thing you're trying to maximize, even though you could write it as f of x, y, z equal to like x times y times z, it's not equal to a number. It is just the thing you're trying to make as big or small as possible. So the constraint, there should always be a something equal to a number typically. And usually we set it equal to 0. Whereas the thing you're trying to optimize is not equal to a number. You're trying to figure out what is the biggest number it can be or what is the smallest number it can be. So let me just point out. Yes, sorry, getting all sorts of things all over the place here. So before we look at, we'll look at that one, but I just want to point out this one here. So this one says, oh no, that's not the one. Sorry, I'm getting this one here. Yes, this one, which was one. Yeah, this is actual exam 1. Sorry. Says the sum of the squares of 2 positive numbers is 18. Use LaGrange multipliers to find the maximum possible value of the sum of these numbers. To me, that feels like it's the most writing that we have to interpret. So I just want to point out, we're trying to maximize, well, actually, so what do we want to call our numbers? Any 2 variables are fine. I would normally pick x and y. So our numbers are x and y. And we're trying to maximize what? Not the sum of the squares. This says the sum of the squares of 2 positive numbers. Oh, they're both positive. X is positive, y is positive. That's good to know. Is 18. That's my constraint. I'll write that down in a second. use Lagrange multipliers to find the maximum possible value of the sum of these numbers. So I'm trying to maximize the sum, which is just x plus y, which is not equal to a number, because if it was equal to a number, then I would know what it was. I wouldn't be trying to maximize it. My constraint here is the first sentence. She should have said but anyway, sum of the squares of two positive numbers, x squared plus y squared is the sum of the squares of those numbers, is equal to 18. There's our f of xy, and setting this equal to 0. There's our g of xy. That is how we would start this problem. So notice that this problem, unlike those other two practice exams, kind of has a lot more reading that we have to do to really even know what the functions are before we start using the process of Lagrange multipliers. If we have time and desire, we'll come back to this one, but let's look at the other one because that's the one that was asked about. So the other one says the following. Let me write on paper that I will actually scan later. So let's write this out. So use Lagrange multipliers. This is from practice exam 1-2. Oh, nope, that's 1-1. Where's 1-2? Sorry. There's so many things to look at here. Apologies. 1-2. Okay, here we go. This one, yeah, this is the one I was identifying as probably the hardest one. So use Lagrange multipliers. Notably, don't use Lagrange multipliers if it doesn't say to. Right? If you're trying to maximize or minimize something, unless you really love using Lagrange multipliers, just do it the other normal way to find the point or points on the surface. Oh yeah, this will be a good time for that picture. Y squared equal to 1 plus x times z, which I'm gonna write z times x because I already started writing something that looked more like a z, that are closest to the origin. Okay. And actually, there's a really good picture that Grant has drawn on these notes that I want to show you. We'll come back to this in a second here. So if we are trying to find the point on the plane, 2x plus 3y plus z equal to 6, that is closest to the origin, here's the idea. Here's the x, y, z coordinate system, kind of actually rotated away from us, or 90 degrees, right? Usually I would be drawing x out towards you and y to the right, but we've rotated this 90 degrees counterclockwise. Here's my plane, and I'm trying to find the point on the plane that is closest or has the minimum distance to the origin. So when someone says closest to the origin, you're trying to minimize the distance to the origin. We want to minimize that, and I imagine she's mentioned in the class, instead of minimizing the distance of something, it is equivalent to minimize the square of the distance, and usually easier. So instead of trying to minimize the square root of x squared plus y squared plus z squared, we are typically going to minimize x squared plus y squared plus z squared. It will give you the same x, y, z coordinates, but if you're trying to find the minimum actual distance, then you do need to go back and square root your result if you plug those back in to find the actual distance between your point and your surface. Usually you're not asked to find that though, so it's kind of moot. The thing I want to point out is one way to think about what's going on in this kind of example is you're just making spheres from the origin that get larger and larger and larger. And we're trying to figure out what's the smallest sphere that we can draw so that it just touches the surface. That point of tangency is the point that'll be the closest to the origin, where that sphere is the smallest it can be while just touching the plane. If it's any bigger, it's going to touch the plane in like a circle's worth of points. If it's any smaller, it won't be big enough to touch the plane. And the thing I want you to know about this is that point there of tangency, well, when a surface is tangent to another surface, they both have the same gradient or directional vector, meaning the gradient of one is equal to a multiple of the gradient of the other, meaning this kind of equation is true. That is actually why we're doing all of this, because when you're trying to find where one surface is like one constraint is met and the other surface is maximized or minimized, you are finding the place where they're gradients point in the same direction or are multiples of each other. Do we need to know that to do this? No. Is it nice to have seen it at least once to kind of have an idea of what's going on? Yeah, it's kind of nice. Okay, so back to this problem. Back to this problem. All right, so I'm trying to, all right, what am I trying to do here? So my constraint, which I usually don't write first, but whatever, I'm going to write it as xz minus y squared plus 1 equal to 0. So subtracting y squared from both sides and then rearranging it. And that's going to be my, my g of x, y, z. My thing I'm trying to minimize, right? Because I'm definitely trying to minimize the distance if I'm trying to find the point that's closest. So I'm trying to minimize the distance squared. So x squared plus y squared plus z squared. I could see her maybe, although it probably makes it a little complicated, asking a question like this, but using a different point other than the origin. So just to point out here, right, this is really x minus 0 squared plus y minus 0 squared plus z minus 0 squared, because it's the distance from my point, x, y, z on my surface to the origin, which is 0, 0, 0. And that thing you're trying to minimize is your f of x, y, z. And now we're going to do the usual thing. We're going to take all, we're going to write L of x, y, z lambda equal to x squared plus y squared plus z squared minus lambda times xz minus y squared plus 1. I'm going to find all the partials, find the critical points, and then try to figure out their maximum or minimum. So Lx is 2x minus lambda z. Ly is 2y. Oh yeah, this is going to be one of those ones where I think we do have to solve for lambda. Plus negative lambda times negative 2y is plus 2y lambda. And then Lz is going to be 2z minus lambda x equal to 0. Yeah. So if I were looking at this one, I would identify the middle equation as the one I should start with. Because looking at that middle equation, I can see a couple things. So using this one, if I factor out a 2y, I get 2y times 1 plus lambda. So here's what this means. It means either y equals 0 is going to be part of my critical point, or lambda equals -1 is going to tell me what all my critical points are. So I'm either getting y equal to 0 or lambda equal to -1. Notably here, y equal to 0 isn't going to affect either of those equations there. In fact, looking at these equations, I can see that x and z are probably going to have to be the same as each other, or close to the same as each other, because there's kind of a symmetry here. If you interchange x and z here, you get that. And if you interchange x and z there, you get, and usually when you're able to interchange two variables and get the other equation from that, that usually means x and z or whatever the two variables are have to be the same. Because if they weren't the same, you could interchange them and they would have problems. So let's work with this though. So let's start with lambda equal to -1 first. So I just use lambda equal to -1. Now I've got Lx is going to be 2x plus z is equal to 0. And Lz is going to be 2z plus x is equal to 0. So I could probably just see that 0, 0 is going to be 0, 0. That doesn't seem right though. Seems there's something wrong, right? So 0, 0 doesn't meet the constraint. That's okay though. So if I look at z equal to -2x, if I plug that in there, we get, -4x. This is why solving for lambda is usually not a good idea. Yeah. Oh, no, we're totally fine. I'm dumb. Sorry. It's okay. I'm not dumb. I just wasn't thinking that clearly. So let's be careful here. Z equals -2x. I plug that in here. I got -4x plus x. Yeah. So I get x equal to 0, which means z is also equal to 0. What about y? We don't know what y is, right? We've only said lambda equals -1. It was lambda equals -1 or y equals 0. We're using the lambda equals -1. So now that we've got z and x, let's use our constraint to figure out what y's got to be. So the constraint is that xz minus y squared plus 1 is equal to 0. So that means that 0 minus y squared plus 1 equals 0. So 1 equals y squared. So y equals plus or minus 1. So far, I've got two critical points. 0, 1, 0, and 0, -1, 0. I will say, to me, this feels like a too challenging problem for an exam, personally. I think this one's a little too hard for LaGrange multipliers. Doesn't mean we can't do it. I'm just saying I wouldn't expect one of this degree of difficulty on your exam where you also have to solve for lambda, because usually that's not always a thing we have to do. Okay, we've dealt with lambda equal to -1. Now let's go back and deal with y equal to 0. So if y equals 0, we're still left with 2x plus z equal to 0. Oh, nope, sorry. My now lambda is not -1. So I'm left with my two other equations. My Lx is giving me 2x minus lambda z is equal to 0. And my Ly, my Lz, holy smokes, 2z minus lambda x is equal to 0. So now I'm going to use this, solve for lambda, to get the things equal to each other. So I'm going to get 2x divided by z equal to lambda. And here I'm going to get 2z divided by x equal to lambda. So those equal to each other, I get 2x over z equal to 2z over x, doing some cross multiplication and canceling the 2's. I'm getting x squared equal to z squared. Back from the initial work I did. So the initial work I said when I was just using this equation here, sorry, you can't see that. I factored out the 2y. I said either y is going to equal 0 or that's going to be 0. And then I started with the lambda equal to -1. Sure. So this, yeah, I'm not loving this, but that's what I've got. So looking back at my constraint is x times z minus y squared, but y squared is 0 plus 1 equals 0. Okay. So it looks like x is equal to plus or minus z, or really plus or minus x is equal to plus or minus z. So let's try one of those things. Let's try setting z equal to x. So if I do that, I'm going to get x squared plus 1 equals 0. No solution. Right? So that's not going to give me anything. Let's try setting z equal to -x. Well, then I'm going to get x times -x, so -x squared plus 1 equal to 0, or 1 equal to x squared. So that's going to give me x equal to plus or minus 1, which means I'm going to get, with y equal to 0, x can be 1, y is 0. And if x is 1, what does z have to be? Sorry. So is it 1 or is it -1? It's not both. It's -1, right? Because we used that z was equal to -x. So if we're saying x is +1, we are also saying that z has to be -1. Otherwise, the point's not on the surface. 1, 0, 1 isn't on that surface. If x and 0 are both 1, you get 1 plus 0 plus 1, that's not 0. So x and z have to be opposite signs, or -1, 0, 1. So those are our 4 critical points. And now to determine which one's the closest, plug them all into the distance formula and see which one gives you the smallest distance. It's going to be these two, because you're trying to minimize x squared plus y squared plus z squared. If you plug these in, you're going to get 1 plus 1, which is 2. If you plug these in, you're going to get 1. So 0, 1, 0 and 0, -1, 0 are the points. Sorry, you can't see that. on the surface, which I should write in the way, y squared equal to 1 plus xz closest to the origin. Because they have the minimum, the smallest distance, which I'm just plugging into the equation without actually writing it down. So again, I think this one's a little, I would not ask a question like this on the exam because I think it requires a little bit too much algebra and it's a little out there. I think, on the other hand, I think the other question that we addressed, where this one, I mean, obviously it was literally on the exam she gave. I think this is a perfectly reasonable Lagrange multipliers question. And I would encourage you to practice it because I could see there being one like it on your exam. She could ask it the other way, right? Find two numbers x and y that add up to 10, and you're minimizing the sum of the squares of them. That's something we could do as well. All right, it is 1:03. Should we do more Lagrange multipliers? Okay, I see a couple of yeses. Let's do one more. Do you have anything in mind? You just want me to make something up? If you have something in mind, I'm happy to look at it.
There's so many different.
Right. What I would say about these ones on the homework, even as far as the exam goes, is I would be less concerned with determining if something is a max or a min. Really, if you're asked to do that on your exam with Lagrange multipliers, what you should do is plug your points into the original function and just be like, well, this one's the biggest, that's the max. This one gives you the smallest value, that's the minimum. There is nothing more really that is reasonable to be asked to task us to do. That's not a very easy thing to do for some of these homework problems, they're just kind of weird. Yeah, what
One that from the mid.
Sure. Well, another Lagrange or something else. Okay, so let's see. The other Lagrange one from the practice midterms. I feel like that one is sure. Yeah, let's look at the one from midterm 1-1. So we want to find the maximum, and then this is from midterm 1-1. Find the maximum and minimum values of f of x, y equal to x times e to the y. That's terrible. Subject to the constraint x squared plus y squared equal to 2. I would encourage you to, again, imagine this similarly to the graph that we graphed on Desmos. You've got some surface, and you're intersecting that surface with a cylinder. And you're just asking, okay, on that surface, where is the cylinder going to have the highest value? Where is the cylinder going to have the lowest value? It's kind of nice when your constraint is this kind of thing, because I think you can have that kind of picture in your head. Like, okay, we're just taking this surface and we're cutting it with a circular cut and seeing, okay, along that cut, where is the surface the tallest? Where is the surface the lowest? Okay, the process is the process.
And I have a question.
Mm-hmm.
You said that there's no like one way to hear about this problem.
You're welcome. Yes.
But I was just wondering, in those general sense, what are the main things
Sure.
that you want to do?
Okay. So first off, we want to identify F and G. So they've already written what F is, and hopefully they've used the right letters. The thing you want to maximize is F, and the constraint is G. So you could say that this is G, but usually what we actually do is we set all of it equal to 0 and then say that the thing that's equal to 0 is G. So really, it's more typical in your class to say, take x squared plus y squared minus 2, set that equal to 0. And that thing on the left, that is your G of whatever variables. Then the next step is to write out your thing, your Lagrange thing. I don't think there's a name for it, but whatever. Your L of variables, comma, lambda. And I'll just say very generically, it is always going to be f of xy minus lambda times g of xy. That is the general thing. Technically, it doesn't actually matter where you put the lambda. You put it times f or times g, but this is the standard way of multiplying by g. So then our L of x, y, lambda, we're actually going to put the functions in there. It's going to be x times e to the y minus lambda times x squared plus y squared minus 2. I would also point out it is usually not in your interest to simplify these functions at all, especially if it's like a distance between a point and a not 0 point. If you've got like x minus 2 squared plus y minus 3 squared plus z plus 1 squared or something, don't multiply those out. The derivative is not hard to do if you just leave them as is, right? The derivative of x plus 3 squared is 2 times x plus 3 to the first times 1, but right? So don't multiply stuff out for these kinds of problems typically. After we have found this thing, then we take our partial derivatives. Lx, Ly, and if you want L lambda, but I will point out again, this is your L lambda equal to 0. Technically, it's the negative of L lambda equal to 0, but you can multiply both sides by -1 and have the same thing. So it's the same thing. So Lx is going to be the partial with respect to x. So 1 times e to the y minus the lambda just hangs out in front for any of the partials that aren't partial with respect to lambda. And the derivative of the inside with respect to x is 2x. Set that equal to 0. Same deal for the next part. The derivative with respect to y is going to be x times the derivative of e to the y is e to the y minus lambda times derivative of the inside here is 2y equal to 0. This is the point where people can go different directions. My usual advice here would be to solve each equation for lambda and set them equal to each other. If it's only x and y, you're only going to have one set of equations equal to each other. If you've got x, y, and z, you're going to set them equal to each other pairwise. So like the first two equal to each other, and then either the second two or the first. Usually we do the first two and the second two, but you can pick any two.
So for these, you would only use these two equations.
That's all we've got.
And then if it's x, y, and z, we would do like the first two or the second two.
Or the first and the third.
Okay.
And the idea here is to get a relationship between the variables we have, because then we're going to take maybe we're going to get like y equal to 7x to the third. Probably not. I'm just making stuff up. But then we're going to take whatever relationship we have and we're going to plug that back into the constraint so that we can have an equation with how many variables in it? How many variables do we want to have in an equation if we're trying to solve it? It's going to have less because I'm plugging in that y is equal to something with x's in it. So we're going to have an equation with one variable, which is great because then we can solve for that one variable. Just like back in the example with x, y, and z over here, right? The first example we did, which I can't now seem to find. Where's the rest of you? Anyway, the first example we did, we had stuff with x, y, and z, and we got x equal to something with y and z equal to something with y, and then we plugged in the y thing for x and the y thing for z, and then we had an equation with just y's in it, and we were able to solve for y. Of course, I can't actually find it now, which is whatever. I'll find it later. It's not important. Okay. So solving both of these for lambda. Now I'll point out you can do this in one step. I'm going to add the lambda times 2x to both sides, and I'm going to divide both sides by what's multiplying lambda. So I think you can reasonably say e to the y divided by positive 2x is equal to lambda. Similarly here, x e to the y divided by positive 2y is equal to lambda. And then set those equal to each other. So now we're going to get e to the y over 2x equal to x e to the y over 2y. And I really can't stress enough. It is usually in your interest to, before anything else, cross multiply. And if you've got like things to distribute, it's usually a good idea to distribute them because usually stuff will cancel. Like you'll get a 2xyz on this side and a 2xyz on that side, and they just cancel out or subtract them both. So here I'm going to multiply both sides by, now, okay, we can cancel the 2's, right? You don't really need to multiply the 2's to each side. But I'm going to get a y e to the y equal to x squared e to the y. But if y e to the y is equal to x squared e to the y, well, y has to equal x squared because e to the y is e to the y. Or in other words, you can divide both sides by e to the y. So dividing by e to the y, you get y equal to x squared. And that's enough. That's a relationship between x and y. I can now take that relationship and sub it back in to my constraint. Yeah, Jocelyn. I don't want to say no. But here's the thing. I could have went and solved x equal to the square root of y or the negative square root of y. And then plug that back in for x. But I'm going to take the easier path. If I, right, and you, I mean, I would generally just generally, I would like to have an equation with x's in it because we like working with x's better because that's what we're used to. So if I can get y as a function of x, I'm usually going to stop there. But we can also finish it the other way as well, just to see that we should get the same thing. So if I plug in y equals x squared, I'm going to get instead of x squared plus y squared equal to 2. Now I've got x squared plus x squared squared equal to 2. So really that's x squared plus x to the 4th equal to 2. Ugh, terrible. Okay, so this is not my favorite, but we need to bring everything to one side. So I've got x to the 4th plus x squared minus 2 equal to 0. And to me, that looks like some quadratic factoring. That's what I did. I'm not sure where you mean. I'm looking at my constraint.
Yeah.
And so x squared plus y squared equals 2. I'm replacing the 1y to the 1st with x squared. But I have a y squared there. So my y squared, my y is equal to x squared, but then it's still getting squared. Am I missing something?
Yeah.
Okay.
Sorry, I can't.
No, it's okay.
I mean, like, since y is equal to x squared. In the constraint.
Oh, why wouldn't I just write y here? Because I'm dumb. That's why. Good call. I like it. Yeah, excellent. No, really good point. You were making excellent point. I am doing this the harder way because I didn't see the clever thing. You are totally 100% right. Or as Jocelyn would have pointed out, if I had done x equal to the square root of y and then plugged in the square root of y for x, I would have gotten y squared plus y equal to 2. So be smart. Sometimes people don't see all the things, right? I was going to try. So just to point out, here's what I was going to do, just so you can see it this way. I was going to factor this as x squared plus 2 times x squared minus 1. But you all smart people there would have brilliantly, I think, done y squared plus y minus 2 equal to 0 and factored this as y plus 2 times y minus 1 equal to 0. Which is, yeah, the way to go for sure. So doing it this way, we're going to get either y equal to positive 1 or y equal to negative 2. Now here's where we have to be, interesting. I don't think y can be negative 2. Oh, question. Well, so because of what Maddie said, so I had this. I had x squared plus y squared. Let's just write minus 2 equal to 0. And I less cleverly said, oh, y equals x squared. So I'm going to substitute in x squared for y. And I'm going to say, okay, x squared plus x squared squared minus 2 equals 0. And that's the way I was doing. And I was getting this. But they said, well, James, you have x squared. X squared is equal to y. So take what x squared is equal to and replace x squared with that. And then you've got y squared plus y minus 2 equals 0. That is also a perfectly fine way of doing it. That's what's happening there. Because we're not saying that x is equal to y. We're saying that x to the second power, which is exactly what we have there. Right. Because it's all right. You could, if you really wanted to do more work, you could have said x equals the square root of y and then plug that in for x and then squared it and gotten y back. Now, the thing to be aware of here is that even though we're getting two different values for y, I don't think one of them is going to work for us because y has to equal x squared. And if y is negative 2, x squared can't end up equaling negative 2. So this, I don't think this part gives us anything. Because if x squared equals negative 2, that's a no-go. On the other hand, this is going to be fine. If x squared equals 1, then x is going to be plus or minus 1. So it looks like our two critical points are x is 1, y is 1, or x is -1, y is 1. And then we want to find the max. So here's the good news about a problem like this. They said find the maximum values. So great. Oh, and they did say to be careful here in a question like this, they're not asking you to say the maximum is at 1, 1, and the minimum is at -1, 1. They're actually asking you what the value, the maximum value is equal to, and then the value is equal to. So here's how I would finish this problem off. I would say, and I remind myself that f of x, y is equal to x e to the y. So f of 1, 1 equal to 1 times e to the 1, which is just e. And then f of -1, 1 is -1 times e to the 1, which is negative e. Which is bigger? E or negative e? E. So I would write then, so I would find both values or all the values, and then write, I would look and see there's the biggest one. Be like, okay, I would write E is the maximum value. And I would down here, I write negative E is the minimum value. But you actually probably need to use some amount of words there to let the person know that you are like saying, oh yeah, that one's the maximum value, this one's the minimum value. The maximum occurs at the point 1, 1. The minimum occurs at the point -1, 1. But nobody asked us to find that in this problem. Yes.
Sorry, how did we get to 1, 1 and negative?
Well, really by what you all told me. So I got y equal to 1, right? And y equal to -2.
Yeah,
But remember, we had that y was equal to x squared. That was the relationship we found between x and y.
yeah,
So once we got y equal to x squared, well, y equal to 1, I said, well, I'm going to replace y with x squared to find the corresponding x value. If x squared equals 1, x is plus or minus 1. So x is positive 1, y is 1, x is -1, y is 1. But then for y equal to -2, well, if I set x squared equal to -2, I don't get any solutions. X squared can't be a negative number. Yeah. No, not at all. Okay, other questions about this? Sure. So let's go back a little bit. So remember, we found the relationship between x and y. So, and actually, I should be a little more clear here. Yeah, that's fair. No, that's that's typical. So often, like with LaGrange multipliers, when we find the relationship between x and y and z, we get like y equals x and z equals 2y or something like that. So it's easy to take whatever you find for x and y, just be like multiply it by 2 or multiply or leave it the same. Like with that first problem where like y was 18 and x was equal to y, so x was also 18, and z was equal to 2y, so z was equal to 36. Here we're doing the same thing. We're using the equations from the partial derivatives to give us a relationship between the two variables we care about. Or the three variables we care about, however variables we care about, not lambda. We don't care about lambda most of the time. So then we're saying, okay, well, for both of these to equal 0, it has to be the case that y is equal to x squared. There is no other way that this equation will equal 0. Great. So then we use that fact in the constraint. We need y equal to x squared. And you all said, James, be smart, replace x squared with y. We did that. Then we ended up getting an equation, y squared plus y minus 2 equal to 0. So we ended up getting y equal to -2 or y equal to positive 1. But then we went back and said, but we know that x squared has to equal y. So if y is equal to 1, then x has to be plus or minus 1. And if y is equal to -2, then x can't be any real number because x can't be a square root of a negative number. So yeah, so basically, when you're doing these Lagrange equations and you're finding like y equals x or z equals 2y or whatever, you should be circling those because those are the things that once you find one of either x or y or z, you're going to plug back into those spots to then find the other x, y, z, whatever's left over. Cool. How much time have we got? We got like 8 minutes left. Are there other questions about any of the practice exams that you would like me to address? because I can. I mean, we could do one more LaGrange problem. I feel like we've done a lot of LaGrange, so we could do something different. Let me take a quick look here. See if I see anything really. Let me look at the actual exam, because I feel like the actual exam is usually just a slightly better barometer of what someone is willing to actually ask on a test. Domain, range, level curves, limits. Sure. Partial channel. Cool. Yep, those don't seem too terrible. I will point out. Yes, I will do so. I just want to point out, I don't see any questions about finding a maximum or minimum over a closed region, like over a square or a triangle, like we did that one day in class. That doesn't mean it couldn't show up, but I'm not seeing any questions like that on, at least on the actual exam. Maybe there are on the practice exams. I didn't look that closely. The other thing I'll point out is looking at the solutions for question 6. It looks like, so specifically for words, question 6b, it looks like she's always asking you to find the direction in which the function increases the most rapidly at a particular point. And we all know that the direction that the function increases the most rapidly is the what? The gradient. Now, looking at her solutions, it looks like she is not ever normalizing her gradients. What do I mean by when I say normalize something? When you normalize a vector, you make it a vector of length 1 or a unit vector. In other words, she isn't taking her gradient and dividing it by its own magnitude. Which to my mind means you don't have to either, but you maybe should, I don't know, check with her or something. I don't know. It just, so, but looking at all her solutions, like one of her vectors was like the vector 2, -3. And that, I mean, it's true. That vector points in the same direction as the unit vector in that direction. So technically, and that actually, that, I mean, to be honest, that is how I would also prefer to answer the question. I think it's kind of unnecessary to have to normalize the vector if you're just saying what direction does it point in. But you might want to ask for clarification. You might be like, do I need to write the unit vector, or can I just write the vector, the gradient, and leave it at that, right? You still have to plug in the point to find the actual numbers for the gradient, but that's what you're being asked to do. All right, but yes, domain and range. Let's talk about it for a second here. So domain and range. Let's see what kind of things we got. That one looks kind of boring. That one looks sure. Trying to see if any of these look particularly off the wall or exciting. No, they're all pretty standard. Okay, let me just. Yeah, okay. Let's look at. Sure. Let's consider the following, and we'll do 2 of these. So domain and range. And we'll look at 2 different functions. I know we only got 5 minutes, but don't worry. So our first function is going to be f of x, y equal to the square root of x squared. Yeah, let's make it, sure. X squared plus y squared. Where'd you go? Where'd you go? Sorry. Yeah. Minus 16 plus 3. And the second one is going to be g of xy equal to the square root of, sure, y squared minus x minus 5. For domain, if you got a square root, all this, oh, that's, they've gotten used to writing with these thicker pens now. All the stuff underneath or inside the square root has to be greater than or equal to 0. If you see x squared plus y squared or minus x squared minus y squared, you need to isolate that thing. So I want x squared plus y squared all by itself. So I want x squared plus y squared bigger than or equal to 16. And then what you should do to graph the domain is think about that as just an equality. Now I was trying to graph x squared plus y squared equal to 16. What kind of shape would I have? Not a parabola, not a circle, right? X squared plus y squared equal to 16 is a circle centered at the origin with what radius? 4. Should I draw that circle as a dashed line to exclude it, or as a solid line to include it? Do I want it to equal 16 or just be bigger than 16? I want to include it because literally the equal sign right there. So when you're drawing your border, pay attention to whether it's a strictly greater than or equal to, sorry, a strictly greater than or a greater than or equal to, and that'll tell you if you should draw it dashed or thick. And then, and this is always how it works, you always get everything on one side of that border. So either all of the inside of a circle or all of the outside of a circle. And the way you test is you just test a point. If I test the origin, which is obviously inside the circle, 0 plus 0 is 0. Is that bigger than or equal to 16? Of course not. So 0, 0 isn't in the domain, and neither is anything else that is inside the circle. My domain is everything that is outside the circle, which you should just do like this. There's your domain, everything outside of the circle. Cool. With this other function, I'm going to start off the same way. I'm just going to take the inside and set them to be greater than or equal to 0. Now, I don't see an x squared plus y squared here. I've got y squared minus x minus 5 bigger than or equal to 0. Normally, I would solve for y, but actually I don't really want to here because solving for y is going to introduce a plus or minus square root, which I don't really want. So usually I would solve for y because I like writing y as a function of x. In this particular example, I would actually solve for x. So I'd probably bring x to the right-hand side and just say y squared minus 5 is bigger than or equal to x. So I'm going to graph x equal to y squared minus 5. Okay, here's how I'm going to think about this. If I were graphing y equal to x squared minus 5, it'd be an upward opening parabola shifted down 5. Now I'm just doing that same thing, except I'm on the x-axis. So it's a rightward opening parabola shifted left 5. Or you could plot the points. If y is 0, x is going to be negative 5. If y, oh, question. I wouldn't recommend that. You could, it'd probably be fine, but someone might miss that you've labeled it that way, or might be like, no, you need to drop the typical way. What I would say is if you want to do that, what you should really do is draw it the other way and then actually reflect it across the line y equals x, which is not really easy to do without like other stuff. But plotting points is not terrible. If y is 1, x is going to be negative 4. If y is negative 1, x is going to be negative 4. If y is 2, x is going to be negative 1. If y is negative 2, x is going to be negative 1. I think we can start to see, right, if y is 3, x is going to be 4. Y is negative 3, x is also 4. So yeah, I think we can kind of see the parabola here. We are including the parabola for the same reason we were including the circle over here. And then if I want x to be less than or equal to y squared minus 5, again, I'm just going to pick a point. If the origin's not on your border, pick the origin. So if I plug in 0 for x and 0 for y, is 0 less than or equal to 0 minus 5? It definitely is not. 0 is not less than negative 5. So again, don't want this stuff here. I want everything out here. Sure. So really, honestly, the way I thought of it was I thought of graphing y equal to x squared minus 5. I know that graph is your usual upward opening parabola shifted down 5. Well, when you interchange x and y, instead of getting an upward opening parabola, instead of getting a parabola that opens in the increasing y direction, now you're getting a parabola that opens in the increasing x direction. And instead of shifting down 5 in the negative y direction, you're shifting left 5 in the negative x direction. You're essentially changing the direction based on it being x versus y. But you could also just plot points. We know it's a parabola. Basically, if you've got y equals x squared or y equals negative x squared, it's opening up or down. If you've reversed them, if it's x equals y squared or x equals negative y squared, it's opening left or right. What time is it? It's 1:32. I should probably stop talking here. I'll just point out since we're almost out of time, since we're out of time, the range here, the smallest this can be is 0. The square root, right? Square roots, you can't ever get out a number smaller than 0. Can I get 0? Yes, I can. X could be 4, Y could be 0, 16 plus 0 minus 16 is 0, square root of 0 is 0. And then you have to add on 3. So the smallest value for my range is 3. And then it could get as big as you want. Y could be 4, and X could be bigger and bigger and bigger and bigger and bigger and bigger and bigger. Over here, yeesh. Again, I think I'm limited by I think the range is actually going to be very, very similar. The smallest this can be is 0. Specifically, if I let Y, I'm just picking points that make it work. Just to see that I can. I don't really have to, but like if Y is 0 and X is -5, 0 plus 5 minus 5 is 0. And the square root of 0 is 0. So definitely my smallest range value is 0. And I can just keep letting things get bigger and bigger and bigger, right? If X is -5, then those parts cancel. You can just let the Y values get larger and larger and larger to get ever increasing numbers for your range. Range is not really an exact process. It's kind of one of those things where you're like, check and see, check and see. Y can be negative infinity. We're not talking about the values that Y is taking on. X and Y are our inputs here. Our output is Z. So we're talking about what the Z values get to be. If you're thinking just like in 2 dimensions where Y is a function of X and X is the domain and the Y values are the range. Now we're thinking of Z is a function of X and Y, and we're thinking of the region in the XY plane as the domain, and the height Z values is the range. So, but yeah, definitely when it's a function of 2 variables, the range is not the Y values. The range is the Z values or the function values. Right. No, it's definitely not. It's a very important and good distinction to make. All right, I should stop there.